Okay, thanks. Yes, I'm Bourne. I've been a postdoc here in Cambridge for quite a while now, working a lot with Deborah and a whole host of postdocs and students on various projects, all related to simulating supermassive black holes. And so, yeah, I've essentially decided to give an overview of a few projects that I've done over the years while I've been here. And I'll say this is more of an aspirational tag at this point, but is hopefully the direction that we're going. So we've heard in a few talks that supermassive black holes are a key ingredient if we want to do galaxy evolution. They move stuff about, they heat stuff up. I think Julie mentioned earlier that they impact the matter power spectrum, although there's not so much agreement between simulations on this, but they essentially are necessary in cosmological simulations to give us realistic looking populations of galaxies and various properties. But as we also heard, something that's fairly clear and simple to say is that there's a huge dynamic range if you're going all the way from the event horizon of your black hole through the various scales up to the cosmic web and back again, because there's processes communicating backwards and forwards between all of these scales. And while it's clear that there's this huge dynamic range, it poses a huge problem when it comes to doing simulations. And this is where you have to make very careful decisions about how you model the outer boundaries and your inner boundaries and use subgrid models. And this has really been one of the motivations of the work I've been doing. So I'm going to start off from the large scales and work my way down. Julie's already given a nice talk previously on this. So looking at jet feedback in galaxy clusters, as we've heard, and I agree that these clusters and groups provide visually the most obvious evidence of AGN feedback through the jets and the cavities they inflate within the hot intercluster medium of black holes doing something to their environment. We've seen this plot a couple of times, looking at the energetics of this feedback and how it correlates with the cooling rate in these systems. But as we've also heard, although this makes things look quite clear in terms of energetics, what's actually going on is much messier, and there's still really an open question as to how this energy is coupled to the intercluster medium. I'm going to flash up this article that Karen Yang and I put out last year that's reviewed sort of the last decade or so of simulation work trying to look at jet feedback in galaxy clusters. But I'm going to focus now on some of the simulations we've been doing here. So all of the simulations I'm going to talk about use a repo. This is essentially a code that uses a moving mesh. And one of the key ingredients for the simulations we're doing is a refinement scheme developed by Mike Curtis, who was a PhD student here in Cambridge a number of years ago. Essentially, if you have a black hole in the center here, and this mesh is modeling your gas, within some region, you force the resolution, the spatial resolution, to improve as you get closer and closer to the black hole. And this was first done to improve estimates for accretion rates onto the black hole, but it also meant that we could essentially piggyback onto this, inject jets at small scales and high resolution, and if we take the resolution with us, we can capture the propagation of the jets, the lobe inflation, and the interaction with the environment. And a lot of work has been done looking at simulations of jets in idealized environments. And what we wanted to do was put this into more realistic environments. And so to do this, we took some Zoom simulations of galaxy clusters. These were run to low redshift with fairly traditional subgrid models for accretion and feedback. And then we did a set of experiments with fixed power jets with fixed lifetimes, but using this high resolution refinement technique so we could capture these lobes being inflated within a dynamic environment. This is showing the velocity field where we have bulk motions and turbulence already in the environment. We have cold gas structures in the center that the jets interact with. And we can start to look at how the lobes inflate and how they inject their energy into the environment. And so this is just a quick overview of one of these simulations. We've got this movie here where this green material is essentially the jet and lobe material inflating these lobes as the jet launches. We can see that this lobe at the top moves across. This is because there's a bulk motion velocity field in the ICM pushing it across. And then this lobe down here ends up interacting strongly with a structure that's moving in and can be disrupted and displaced. And we've did these simulations for a few different energies. These are some example mock X-ray observations where we can get these rims where material is being compressed by the inflation of the lobes and the cavities, and some mock radio observations as well. And I mean, the picture that we got from these simulations was fairly simple, that when you have the low power jets, the lobes they inflate are more susceptible to this cluster weather, can be readily mixed and redistributed within the system, and then the higher power jets, the lobes live much longer and they drive stronger shocks and can heat the ICM through this shock heating. Now, one caveat with this first set of simulations was that we didn't include any magnetic fields in the ICM, but we know that they should be there. So more recently, we've rerun these simulations, and this is work that I'm currently analyzing, but I think the cleanest and simplest comparison is these two panels here. This is when we don't have magnetic fields in the intracluster medium, and essentially the lobe succumbs to instabilities and is readily mixed into the intracluster medium. And then when we include these magnetic fields that drape over the lobe as it rises through, we retain this low density, smooth lobe structure that can survive much longer. Now, if we look at this one here, this is this lobe up here. The structure up down here is much more complicated. As in the previous simulations, we still had this substructure coming in, and it can still do some damage in here. But the magnetic fields are still clearly potentially very important. Okay, but these works were all fixed power jets for fixed duration. We want to couple the jets to accretion. This brings me on to a model developed by Davide Fiacconi, who was a previous postdoc here, who developed an accretion model that tracks not only the black hole mass evolution, but its spin evolution. And this is done by assuming you have a Shakura-Sunyaev accretion disk that can interact with the black hole and evolve both the black hole spin magnitude and direction. And our previous PhD student, Rosie Talbot, then coupled this to the jet model, assuming a Blanford's-Knight mechanism, which from GRMHD simulations, you can get a spin-dependent jet efficiency. You can set the jet direction by the black hole spin. And she did a bunch of simulations, for example, looking just at the simple jet structure perpendicular to some circumnuclear disk, or if you fire the jet into the central disk structure, you end up with this multi-phase outflow being produced that you maybe wouldn't associate with classic jet feedback. But you can also see that the black hole spin here has ended up being torqued towards the perpendicular direction by accretion of material from this larger gas disk. And then more recently, this year, this came out. This model was included in an idealized galaxy merger simulation. So these are just a few different times of this simulation as the galaxies eventually merge down here. And looking at, for example, the feedback that stimulates the formation of cold gas within the hot halo that can then rain back down onto and feed the black hole. This material actually ends up torquing the black hole spin, so that for one of the black holes, so it starts moving towards the plane of this disk galaxy as well. So you can your black hole spin doesn't necessarily have to be perpendicular to your larger scale galaxies. Also looking at the star formation, where we see some suppression, but not necessarily a rapid quenching merger, at least not during the time scale of the simulation. Okay, and in the last few minutes, or however long I have left, we'll go down to, I think Mitch's 3 minutes, okay. Including questions, okay. I'll go down to slightly smaller scales. So as we've heard, when galaxies merge, the black holes in their center can move to the center of the newly formed galaxy on parsec scales, form a binary. And if you're in a gas-rich environment, you might end up with a circumbinary disk. So we did a bunch of simulations with different binary, a few different binary parameters of self-gravitating circumbinary disks, including inclined cases where the binary is at 45 degrees to the circumbinary disk. We include the refinement technique around the black holes. This is comparison with and without, which means we can capture these mini disks and the streams that feed them. And these are important when we're looking at the gravitational torques that act on the binary. These gravitational torques, we find, in all the cases we've studied at least, dominate for the evolution of the binary and driving it towards merger, helping to shrink the binary. And then the last bit on here I just want to talk about is we've also included this subgrid accretion disk model that tracks the black hole spin. So this means we can look at how the spin evolves and how the spin alignment evolves during the evolution of the binary. And this is interesting because the alignment or misalignment of the spins has an impact on the recoil velocities that you'll get at merger. And interestingly, in our simulations, we find that even at low mass ratios, we don't inhibit accretion onto the primary. This isn't seen in all simulations. And we find fairly short alignment timescales for all of the systems. This is the alignment between the black hole spin and its own accretion disk. And this, we always find, is typically smaller than the binary in spiral time, so we'd expect the black holes to be aligned and hence low recoil velocities. The only caveat to that is when we have initially misaligned systems, and in this case, this is some of these down here, the mini disk angular momentum can vary quite a lot, and the accretion disk angular momentum can vary quite a lot. And you start to see that the spin alignment isn't necessarily as clean as in the coplanar systems that we have, but I think there's still a lot more physics to explore here and a larger parameter space to look at as well. So I think I'll just put up my conclusions and take any questions.
We'll take one or two questions, but I've been informed that several of you have agreed to do Vox Pop interviews. And I'm supposed to ask you to come down here after we're finished. Those are Neil Turek, Aaron Cara, Andrew Conson, Keith Hawkins, Sarah Seeger, Jan Eldridge, Emma Ryan Weber, Leisha Verde, and Sarah Markov. So, questions? Yeah.
Thanks. In your binary simulations, did you also find situations in which the binary actually softened? It outspiraled rather than inspiraled?
Not in any of the simulations that we've done. I know there's varying results in the literature. There seems to be affected by a combination of how thick the disk is, how you model the viscosity. There's been a few parameter space studies on this, but yeah, I think that's another area that needs exploring. Yeah.
Yeah. So, Martin, very nice one. Thanks.
Thanks.
In your cluster simulation, do you include thermal conduction? And do you think that will impact on how you couple the voltage to the cluster?
Yeah, so we don't include thermal conductions in the simulations we have. This is an interesting question. There's been a few works, I know, looking at these simulations in idealized cases. And looking at the the HBI instability and things like this. I think there's a potential role, but I'm not sure if it's a dominant one. Yeah.
There are no more urgent questions. We'll wrap up now, and we have poster session and drinks and nibbles out in the common area. Thank you.